This problem says to sketch at least one cycle of the graph of the cosecant function. It gives it to us here, cosecant of 2x minus pi over 2. Determine the period, the asymptotes, and the range of the function. So the first thing we need to do is think about what does the cosecant function look like. And the cosecant function is the reciprocal function of 1 over sine. So a lot of times when we're graphing a cosecant function, we like to think about the sine function. And these should just be graphs you should pull from memory. And so from our memory, we are going to pull the fact right here that the cosecant function, there are these little parabola shapes. The green thing right here is the sine function. And every time that the sine function has a value of 0, our vertical asymptotes are going to be there, because cosecant is the same as 1 over the sine. So think about when the sine of x, so the cosecant of x, think about when the sine of x is 0, 1 over 0 is always going to be undefined. So every time that this sine curve has an x-intercept, that is where our vertical asymptotes would be. So this would just be the cosecant of x function, but we don't have the cosecant of x. We have the cosecant of 2x minus pi over 2. If it was just cosecant of x, the period would be 2 pi, which means it would repeat itself every 2 pi. So it's kind of hard to see here, but this is pi halves. So this is pi right here, and over here would be 2 pi. So it repeats itself every 2 pi, and the asymptotes of the original cosecant function happen every pi. So if we were listing the asymptotes in equation form, we'd say that x equals, you could say 0, you don't really have to, but 0 plus k pi, where k is every integer because it repeats itself every pi. Well, something is different with this function up here. Its period is not 2 pi anymore, and we can find out what the period is by factoring out something in front of the x. So once we've written this in its factored form, because I can factor 2 out, I want my x to be all alone. That will leave me with pi fourths on the inside of the function. So this number out here gives us what our period is, but it's not 2. We take that number and we take 2 pi over that number. So 2 pi over that number is now pi, which means our cosecant function has been, it's kind of been squeezed together. Instead of repeating itself every 2 pi like it normally would, it's just going to repeat itself every pi. And that's again because we had to factor this 2 out. That 2 affected our period. So it slows our period down to a period of pi. So if I take each of these and call them pi, now it's going to repeat itself every pi. So these little u's are going to be a little bit more squeezed together. So let's say that's 1. So it's going to look, this is C, that's -1. It's going to look something more like that. And our asymptotes now, if I can get them on here, where are they going to be happening at? They're going to be squeezed together as well. Instead of happening every pi, like they used to, now they're happening every pi halves. So you have to take into account if the period has changed if you're trying to find your vertical asymptotes. So the period did change. The period now is x equals, well, the period is pi, and the asymptotes now are at every 0 plus pi halves. Okay, where k is an integer, because they repeat themselves every pi halves. Again, because these U-shapes are repeating themselves every pi. So now that we know that the period has changed and our asymptotes have changed, now we just have to take into account this phase shift. So this phase shift is whatever you add or subtract on the inside of the parentheses here moves our whole function either to the left or the right. And so when we've subtracted pi fourths on the inside of the parentheses, it shifts everything to the right that amount. So now this whole graph is going to shift to the right by an interval of pi fourths. So if we were to draw this again, and I'll just sketch it really, really fast. Here's pi halves, here's pi, 3 pi halves, and 2 pi. The asymptotes used to be, and I'll just use a straight line, it won't be dotted, but we'll know that the asymptotes. The asymptotes used to be at 0, at pi halves, at pi, but everything's been shifted now to the right, pi fourths. So this asymptote now is going to be at, starting at pi fourths, and then again at 3 pi fourths, and then again right here. So everything just got shifted to the right pi fourths. So our asymptotes are now going to be at x equals pi fourths is our first one, plus it's still every pi halves that repeats itself. So this one should have been red. Anyway, so this would be the equation of our asymptotes. And once we have our equation of our asymptotes, we can put in our function. It's going to be really kind of messy here, but they're all squeezed inside here. Let's say that's 1, that's -1. So they're all squeezed, whoops, inside these asymptotes. So a better picture I'll paste right here from the work would be these. It would be these red little U shapes here. But see how that the asymptotes all fall at pi fourths, and then again at a half of a pi greater than that, and a half of a pi greater than that. The blue curve here is the sine curve for sine of 2x. Minus pi halves. So that would be our final graph. The period we know has changed to pi. The range would be up and down ways on the graph. How low does this graph get? It gets as low as -infinity, and then it gets up to -1, and then it starts again at +1 up to positive infinity, and I guess these would be square brackets because we do include the one that it's at. All right, so I hope that helps.